everyone. We're very lucky today to have Aylin Caliskan-Islam here to speak. She's a postdoctoral research associate here at CITP who works in security and privacy, and she'll be talking to us about de-anonymization through analyzing coding style, which I think got picked up in Scientific American recently, right?
Yes.
So it's pretty cool, and I'm excited to hear the talk. Thanks, Aylin.
Thanks for the introduction, Joanna. Hi, everyone. Thanks for coming to my talk. And I'm Aylin, and I'm a CITP fellow and a postdoctoral research associate here. And I usually work closely with Arvind. And today I'll be talking about code stylometry and how we can use code stylometry to de-anonymize programmers. And at the end of this talk, we'll be able to see that style, coding style that's expressed in source code can be quantified and also characterized so that we can study properties of programmers. And what is stylometry? First of all, stylometry is used to uncover stylistic fingerprints, and it has been applied to, for example, fine art by looking at brushstrokes of artists. Or it has been studied in music, for example, the tones and the rhythms that the musicians are using. And in the past, we have also looked at unconventional text. And by unconventional text, I mean text that's found in underground cybercriminal forums, which are a mixture of languages and product information, such as stolen credit card information and account information. And we were able to apply stylometry to underground forum text to de-identify the users in these forums. We have also looked at translated text to see if we can find stylistic fingerprints in translated text so that we can identify the author of the text. And for that, we took English natural language text and translated it to German and then to Japanese and then back to English. And we were still able to observe the stylistic fingerprints in the translated text, and we were able to de-anonymize the authors with high accuracy. And we have been receiving this question. We are looking at natural language, but what about programming languages? Can we also see stylistic fingerprints in programming languages? And I will start by giving an example about how we can use stylometry. For example, there was this book that came out like last year or a few years ago, and it's called The Cuckoo's Calling, and it's by Robert Galbraith. And someone suggested that the book really looks like it has been written by J.K. Rowling, the author of the Harry Potter series. And after that, by performing stylometric analysis on the book and looking at J.K. Rowling's previous books, they were able to prove that with stylometry, the book actually belongs to J.K. Rowling. So J.K. Rowling was just using a pseudonym, a pen name under the name Robert Galbraith. And when I start talking about stylometry, looking at previous text from someone and looking at test documents, I want to introduce you supervised dieallometry, which is possible with supervised machine learning. And how do we do this? So this talk would be mostly about machine learning, and most of the parts would be about supervised machine learning, where we have a closed set of suspects and we know their documents. And let's say that you're given a document. It's an anonymous document. You want to find out who it was written by. And because of that, you also collect documents from a suspect set that this anonymous document might belong to, and then you train a classifier on the suspect set documents, and then you try to find out who this anonymous document was written by comparing stylometric fingerprints. And let's think of a common scenario. So there's Alice, the anonymous blogger, and there's Bob, the abusive employer, and Alice is blogging about the abuses in Bob's company. And she's doing this anonymously. So she's using Tor, and at the same time, she is using a pseudonym. But then Bob, since he's abusive, he's going to go and get everyone in his company's writing samples. And then he's going to train a classifier on that so that he can identify who the anonymous blogger Alice is. And today, I'll be talking mostly about de-anonymizing programmers by looking at their coding style, and also coding style that is preserved in executable binaries. And this has been joint work with a bunch of great collaborators, and it has been published in Usenix last year. So we got the question, what about programming languages? Can we observe style in the programming language in source code. And when we think about this, first of all, everyone learns coding on an individual basis. And as a result, everyone ends up coding with a unique style. And that unique style becomes a fingerprint, which makes these programmers de-anonymizable. And at the same time, by studying coding style in code, we might be able to gain some software engineering insights. For example, how does coding style change over the years? What is the difference between the coding styles of advanced programmers versus less advanced programmers? How does coding style change when you're trying to implement sophisticated functionality as opposed to a very common programming task? And at the end, our ultimate goal is to be able to identify malicious programmers by looking at stylistic fingerprints. I'll talk about two security-enhancing scenarios now. The first one is the common authorship attribution problem. Who wrote this code? Let's say that Alice is analyzing a library and she finds some malicious code in that library. And Bob has a collection of code with known authors. So Bob is going to search his collection to find out who Alice's adversary is. Another scenario is about plagiarism. Let's say that Alice got an extension to her programming assignment, and Bob, the professor, once he receives Alice's programming assignment, he wants to compare it to all the other students in the class and look at the stylistic fingerprints to determine if Alice cheated or not. These two examples were security-enhancing examples, but unfortunately, security-enhancing techniques can be privacy-infringing. So whenever we are trying to use a machine learning classifier to find out something, we have to be careful about what conclusions we want to make from the classification. For example, this is Saeed Malikpour in the picture, and he was sentenced to death because he was identified as the web programmer of a porn site. And in this case, we can see how such methods can be very privacy infringing. But we are not saying that you can just take this method and directly apply it. There is still a long way to get there. Now I will start with comparing our work to previous work so that you have an idea about how we are improving the state of the art here. There hasn't been too much previous work in this area, and the accuracies that were reached were not very, very high. But we were able to change that by bringing a richer representation of stylistic fingerprints to analyzing coding style. And we use syntactic features in order to represent coding style. And this hasn't been used in the past before. In the past, coding properties have been represented with like lexical or layout features. And at the same time, we used a random forest as a classifier, which was a good classification algorithm for our classification task. In the past, we have seen that the highest accuracy that was reached was 97% to de-anonymize 30 programmers. We are able to reach 98% in de-anonymizing 250 programmers. So our method is scaling to larger data sets. In the past, the largest data set that was used had 46 programmers, and they were able to get 76% accuracy. In our case, we scaled the approach up to 1,600 programmers, and we are able to get 94% accuracy. So we can see that we are improving the accuracy, but at the same time, the magnitude of the data set size is also getting greater. I'll give an overview of our method. So first of all, in order to experiment with coding style and evaluate our method, we need to collect a data set. And for that, we picked Google Code Jam, which is an annual programming competition. And I collected coding samples from thousands of programmers from Google Code Jam. And once we have the source code with known authors from Google Code Jam, we pre-process it with a fuzzy parser to obtain the abstract syntax trees. And once we have the abstract syntax trees that represent the syntactic structural properties of code and also the source code, we extract features that represent individual coding style. And we feed these features to a machine learning classifier, in our case, a random forest. And this machine learning classifier has 300 trees that are doing majority voting so that they can classify an anonymous coding sample as it belongs to one programmer. And we chose Google CodeGen because we had a lot of data from the years 2008 to 2014. And at the same time, the programmers were implementing the same programming tasks at the same time in a limited time, which means that most of the difference between the coding samples was the coding styles of these programmers, since they are implementing the same functionality and they have a limited time so that they cannot go back and make their code beautiful, or they like copy paste some stuff from Stack Overflow and so on. And at the same time, the problems are getting harder as you are able to implement a correct solution to a programming tasks. As a result, we are able to control for the difficulty of the problem level, and we can also kind of differentiate between programmers who are more advanced by looking at the ones that were able to complete more rounds. And C++ was the most common language, so as a result, we chose C++ as our ground truth data set. And in order to extract features, we have to understand how we can represent coding style by extracting coding properties from source code. So for that, we started with simple properties. Like, we have our source code, so we went ahead and calculated the properties such as like the layout, the spacing, where do you put the curly brackets, and so on. And then we looked at lexical features. These are things like how you choose your variable names, your function names, or what your comments are, and so on. But both of these features, both lexical and layout, they are very easy to change features. So if you want to obfuscate or hide your style, layout and lexical features would be very easy to refactor. But once we pre-process our data set with the fuzzy abstract syntax tree parser yarn, we get the abstract syntax tree, which represents the structure of the program. So these are more embedded properties of the coding style, which are not very easy to differentiate by just like looking at the source code. And from the abstract syntax tree, we extract coding properties such as the abstract syntax tree node and the abstract syntax tree node bigrams, which are the two nodes that are connected to each other. We look at how deep on average the nodes are. For example, how deep do you put your for loops or like your certain variables. And we also looked at term frequency, inverse document frequency for nodes, which can differentiate between authors that use particular abstract syntax tree nodes. And once we extract the features from the source code and the abstract syntax tree, we feed it to a random forest. And we chose a random forest because by its nature, it avoids overfitting. And at the same time, it's a multi-class classifier as opposed to like a two-class support vector machine. And we perform cross-validation with our random forest classifier. And once we have our method and our features and our parameters, we validate our method on a set of authors that were different than the main data set to make sure that the approach is not overfitting to the authors that we have. And I'll start talking about common cases with different machine learning settings here. So the first case is, again, who wrote this code? Authorship attribution. We want to find out who this anonymous programmer is. And in this case, the anonymous programmer might be Satoshi Nakamoto, the founder of Bitcoin. And in order to experiment with this setting, we took 1,600 programmers, and then we trained on 8 files from these 1,600 programmers. And then we took their last file, the 9th coding sample, and we tested on everyone's coding sample. And we did this until we were able to test the entire data set, which consisted of 14,400 coding samples. And at the end, we were able to correctly find the authors of these 14,400 coding samples with 94% accuracy. How would we do this if we wanted to find out who Satoshi is? So let's say that you have a suspect set in mind that you think might be Satoshi Nakamoto. So you go out and find their source code samples, and then you train a classifier on the suspect set's source code samples. And you also have Bitcoin's initial Git repository, initial Git source code. So you take that as your test sample, and then you test the classifier to see who this Bitcoin code belongs to. So in our case, we had a suspect set in mind, but unfortunately, the main suspect did not have any public source code samples. That's why we cannot really perform this experiment because of the limitation. What if a programmer tries to obfuscate code? So why would someone obfuscate code? For example, malware authors obfuscate code so that the malware becomes unrecognizable and they cannot really tell what the functionality of the code is. We have seen that once code is obfuscated, especially with like off-the-shelf common obfuscators, it does not affect our authorship attribution method. And one example to this is the common off-the-shelf obfuscator Stanix. So we took Stanix and we obfuscated code. And here we can see that all comments are stripped, all spaces are removed, all variable names are refactored, all numbers are refactored with a combination of hexadecimal numbers, and then all characters are replaced with their ASCII representations. So this code becomes unreadable. We cannot really tell what's going on here, but at the same time, the structure of the program still remains the same because only the lexical and layout features have been changed. Since our feature set incorporates syntactical features to represent coding style, we are able to de-anonymize programmers of obfuscated code with the same accuracy as we can de-anonymize their original code. What if we try to experiment with a more sophisticated obfuscator, such as the Tigress visualizer? Here we have 15 lines of code. Once we obfuscated Tigress, again, all the lexical and layout features are changed and refactored, but at the same time, the structure of the program is also modified. But the functionality at the end still remains the same. Unfortunately, the 15 lines of code becomes like 500 lines after this obfuscation, and it runs 9 times slower. And if you're an open source contributor, open source software contributor, like for example, if my collaborator contributes code like this to our project, I don't think I would be very happy, or my other collaborators would be very happy about this. And also it looks sketchy, like what's going on here? This obfuscation is better at anonymizing the code, but it still doesn't perfectly anonymize these programmers. For example, we took a data set with 20 programmers in C, and then we are able to de-anonymize them with 96% accuracy. But once we obfuscate their code with the Tigress visualizer, we can de-anonymize them with 67% accuracy. So there is some anonymization happening, but at the same time, given that the random chance of correctly identifying 20 programmers is 5%, 67% is nowhere close to being anonymous. So we see that obfuscation is not the answer to anonymizing your code. And another case is we can set up a machine learning setup where we can automate copyright investigations, for example. There was this case with Jacobson and Katzer about the Java model Railroad interface. And Jacobson was developing open source code with a copyleft on it. And then Katzer took this and tried to put a copyright on it and make it commercial. And after that, Jacobson claimed that it's a copyleft code. He is the one that has first written it, so Katzer cannot do this. In this setting, what we can do is we have a 2-class machine learning problem. So we're going to take Jacobson's previous code, also Katzer's previous code, train a classifier with 2 classes on those code samples, and then we take the new code that is being disputed, and we can test who it belongs to among these 2 classes. And at the end, it was resolved, and it was seen that the code actually belongs to Jacobson. In this case, we came up with 80 different 60 different pairs of authors to test this experimental setting, and we were getting 100% accuracy in correctly identifying the code from these 2 classes. Another case is authorship verification. Let's say that you work in a company and you have a code sample and your boss thinks that it was not written by you. And in this case, what we can do is we can try to verify it with a 1-class, 2-class approach. And here the first class would be Mallory. Mallory is the employee that claims the code has been written by her. And then we have the second class, which is the outside world. And we train a classifier to represent Mallory, the employee, and also the outside world. world. And here we take samples from Mallory's previous code, and we also take samples from random programmers, which would represent the outside world. And then we take the test sample, which is being disputed, and we try to attribute it and see if it really belongs to Mallory. In this case, we had 80 different sets of such experiments, and we were able to get 91% accuracy in correctly verifying that the code belongs to Mallory or it belongs to the outside world. And one example for this would be that, for example, Zuko tweeted recently that I just heard from an intern at Apple that they disallow her from contributing to open source on her own time. That's illegal, right? So, like, if you're an intern at Apple, and let's say that there is an open source sample, and at Apple they think that it has been written by you and you're not supposed to do that, such a verification method can be used to actually check if it was really written by you. But at the same time, there's another aspect to this. Is this illegal? Can they really enforce and make sure that you cannot do this in your own free time? So this is a discussion point that we can talk about after the presentation. And we were able to see after our analysis that advanced coders have a more distinct coding style. We are able to de-anonymize more advanced programmers with greater accuracy. And again, this brings up this question. Some of us, also in this room, have been contacted by Google from our GitHub accounts for a job position opportunity. And then, this makes us wonder, are companies studying our public code? Are they analyzing it? And are they using this to make employment decisions? And at the same time, we would like to know what kind of decisions are being made by us with our public information. But in this case, it's very difficult to tell because here we have Google and GitHub. The data is on GitHub, and Google is using the public data from GitHub maybe to make such decisions. But we don't know the details about it. We have talked about source code. So when we look at source code, we can kind of tell what's going on. Maybe there are some identifiers in it, like comments, and people pick certain variable names, function names, and so on. What happens when we compile code? So we have binaries, and binaries consist of zeros and ones here. And once we look at this, it's very difficult to tell what's going on here. So we have to apply some reverse engineering methods to better understand what this code is representing. So we wanted to see if coding style is preserved in executable binaries. So after compilation, does style persist? And for this, we have our current work, which is under submission. And now I'll talk about this in the second part of the talk. Why would we want to find the author of an executable binary? First of all, we would like to study if coding style persists in compiled code. Is it getting transformed? Is it remaining the same? What's happening to it? And another thing is, if it persists after compilation, how much of a threat is it to privacy and anonymity? How well can we de-anonymize executable programmers from their executable binaries? And at the end, thinking that most malware comes in executable formats, can we actually identify the authors of malware, or can we do malware family classification? And to answer these questions, we started looking at executable binary authorship attribution. And there has been one main related work in this area. So we can see that this work by Rosenblum et al., they take the binaries and then they disassemble them to get the assembly instructions, and they also obtain the control flow graphs by reverse engineering them. And once they have these, they try to calculate which coding properties represent individual coding style, and then they use a support vector machine to de-anonymize programmers. So in our case, we are trying to bring in a richer representation of coding style. So for this, we use the same data set as they are using so that we can directly compare our results to theirs. And we take the binaries, we disassemble them, and then we get the assembly instructions. We extract features from the assembly instructions. We also decompile the code. And once we decompile the code, we have decompiled source code features, which we had in the first part of the talk with the abstract syntax tree features, lexical layout features, and so on. We also generate the control flow graphs of these binaries, and we extract control flow features. And once we have all of these features, we calculate their entropy to see which features represent individual authors. And then we feed these important features or features that represent author style to a random forest classifier again, and then we de-anonymize the programmers. And assembly features are things like, for example, the assembly instruction unigrams or bigrams, or we can also take the 2 consecutive lines. And the syntactic features are similar to what we had in the first part for source code authorship attribution. Here we take abstract syntax tree node unigrams or abstract syntax tree bigrams, the nodes that are connected by an edge. Also, we calculate the depths of the nodes. And for control flow features, we take control flow graph node unigrams and again control flow graph node bigrams, which are the 2 nodes that are connected with an edge. And once we extract all of these features from 100 programmers, 9 files, each have 9 coding samples, we end up with 700,000 features from these binaries. And once we apply information gain to this, we reduce this feature set to 1,600 coding style features. And again, I'll compare it to related work so that we have an idea about how we are improving the state of the art here. For example, in the past, Rosenblum had the highest accuracy with 77%, and his data set had 20 programmers. And in our work, we have 600 programmers, and we get 78% accuracy. And at the same time, I would like to point out that Rosenblum is using more training samples in his data set, which means that his machine learning classifier has a better representation for training samples because he has more variety there. And we see that, for example, Rosenblum with 20 programmers, he gets 77% accuracy, but we get 94% accuracy in that case. And with 100 programmers, they get 61% accuracy, whereas we reach 92% accuracy. And the largest data set that has been used in the past has only 191 programmers, and they get 51% accuracy. In our case, with 191 programmers, we get 86% accuracy, and we can scale the approach up to 600 programmers, and we get 78% accuracy. So what happens, like, let's say that we have 100 programmers and we know that we can de-anonymize them with 92% accuracy. But let's say that you want to reduce your suspect set size with higher accuracy and then you want to do some manual investigation on that. So for this, you can do relaxed classification with the machine learning classifier. And let's say that your n is 10 and you want to reduce your suspect set size to 10. In this case, once you run this algorithm on 100 programmers, with 98% accuracy, the correct author would be among those 10 suspects that we are left with after the classification. So this can be one way to deal with large data sets. And we are able to scale our approach to 600 programmers, which hasn't been done in the past. And we see that the accuracy is decreasing gracefully. So it's not being affected way too much with the scale getting larger. We wanted to understand how this is happening in binaries. So when we look at binaries or when we look at decompiled code, we cannot really see anything that was in the original code. It's very difficult to tell how we are able to still de-anonymize these programmers. So since we cannot make a one-to-one comparison between the decompiled code and the original code, we decided that we're going to come up with a machine learning method or setup so that we will try to predict original features in the original source code by using decompiled code features. So for that, we took all the test samples we had in our data set, and these are just numeric representations of coding samples. And then in this sample, each value is one feature. Let's say that it's like how many for loops you have. And then we took these instances and tried to predict how many for loops there are in the original sample. And by trying to predict all the features in the original samples, we were able to get a similar representation of these features, and we try to measure the similarity with cosine distance. And for this, we saw that the average cosine distance between the predicted features and the original features was around 80%. And when we compare the original features to directly decompiled features, we see that the accuracy or the cosine distance is 35%, which is much lower. So this is showing us that like original features are being transformed once they are compiled, but at the same time, somehow they still remain embedded there. And it's very difficult to tell how they are being transformed or embedded, but seeing that we are able to predict them shows that there is something that persists there. Now I would like to talk about some real-world scenarios. For example, in the real world, usually people optimize code. Like when they're compiling, they choose different optimizations. So we would like to see how the optimization is affecting the de-anonymization accuracy, because optimization is kind of like obfuscation, because it's normalizing most properties so that it can make code smaller and faster and more efficient. In the second real-world case, we will look at obfuscated binaries. So for example, like once you see malware in the wild, it's usually obfuscated so that you can't understand that it's malware. And also we wanted to analyze what happens with binaries in the wild. For example, what happens with open source contributors, like GitHub contributors? Can we still de-anonymize them even though their data sets are usually very noisy? We cannot really rely on the ground truth of GitHub code, for example, because they take a lot of code from third parties, they use a lot of libraries and so on, but we still wanted to see what happens. I'll start with compiler optimization. So in this case, we took a 100 programmer data set, and then we are able to de-anonymize this data set with 90% accuracy. And then we applied optimizations while compiling, and we had the level 1, level 2, and level 3 optimizations, and we see that our accuracy drops to 86% after these optimizations. So this is a very surprisingly small drop in accuracy after all those optimizations. And then we also stripped the symbols from the binaries, and symbols represent things like the variables in the source code or the routines that we have in the source code. And the accuracy drops down to 67% in this case. Okay, the accuracy is lower, but again, I would like to remind that for a 100 class machine learning problem, the random chance of correctly identifying the author of one file is 1%. So 67% does not mean that it has been anonymized. And then we wanted to see how obfuscations affect the binaries. For this, we chose an open source obfuscator, OpenLLVM, and we applied all the possible obfuscation options they had. For example, like the instruction substitution or introducing bogus control flow to the binaries or control flow flattening. And these are things like, for example, like you can have a set of instructions in the binary, but at the same time, you can replace these with different instructions that would have the same functionality. By replacing or substituting the instructions like this, you introduce new instructions, and like you get rid of the ones that some of the ones that you had, and so on. In the second case, with bogus flow insertion, here we have our code, but then we introduce some bogus code to it, and it's legit code, but it doesn't get executed at runtime by the binary. So once we try to analyze the binary, we will see these properties in the control flow features or in the disassembly features, but they are not actually being used by the executable file. And in the third case, we looked at control flow flattening. Here, we look at, for example, the control flow blocks in the control flow graph. And we take these control flow blocks and we put them at the same level. So they are not nested anymore. And we just use them with switch statements instead of having them nested in the original version. And this is what it looks like at the end. Let's say that you have just a few lines of code, a while loop, but like once you flatten the CFG, you introduce the switch statements and the code gets longer and more complicated. And the same happens to the control flow graph as well. And by applying these, we were able to see that these obfuscations are not actually anonymizing the binaries as well. Our original accuracy with this data set was 90%, and once we obfuscated the code, the accuracy dropped to 86%. And this doesn't show that obfuscation can really anonymize these programmers. And there are some reasons behind this. For example, once you introduce control flow, like bogus control flow, the features that are unique to programmers are still remaining there. So you're not really removing the unique features. And the most effective part here is most probably the instruction substitution, where you're actually messing up with instructions. But again, it doesn't seem to be the best way to anonymize programmers. And what happens when we try to de-anonymize open source code developers? And for this, we collected a data set from GitHub, and we had some requirements while we were parsing GitHub. For this, we looked at like how many stars the repository has, or like how many lines the code has. And we wanted to make sure that the repository has been written by only one programmer. And at the end, we were able to collect 161 programmers based on our seed programmers and repositories that we started searching GitHub with. And we had 2 to 344 files from each of these programmers. Once we tried to compile these binaries to generate our data set, we saw that there is no easy way to do this. So I didn't sleep for a few days, sat down there, tried to compile hundreds of repositories, and we ended up with 90 programmers with hundreds of repositories. And some had like 2 binaries at the end, and some had 20. So we eliminated the ones that had less than 5 and more than 15 binaries, and we were left with a data set of 50 programmers from GitHub. And once we tried to de-anonymize them, we got 61% accuracy in correctly de-anonymizing these 50 programmers. And again, I would like to remind that like these are noisy data sets because there is no real way of proving that the code or the produced binary definitely belongs to the GitHub contributor. So this is a promising step towards applying programmer de-anonymization in the wild. And maybe with some more improvements, it can be used in practical scenarios. Again, we were able to gain insights with binaries as well. We observed that more advanced programmers' binaries had more distinct coding style preserved in them. So this is showing that like coding style is preserved in binaries, but at the same time, if you're an advanced programmer, it persists even more as opposed to a less advanced programmer. And for future work, we would like to look at how we can de-anonymize collaborative work. This is a very common question that we get. Everyone is like, oh, open source code repositories are written by many contributors, so your technique is very limited to just one author. It's just a different setting, having that many authors or programmers and looking at a different open source code repository. And it's important to be able to detect how many programmers were involved in one piece of software, or how we can differentiate between their codes within the software. And we are interested in anonymizing source code and also executable binaries, because here we are showing you that we can de-anonymize them with great accuracy. But there's a countermeasure to this. Like, we are able to de-anonymize them with a machine learning method. If we reverse this machine learning method in a particular way to make sure that the identifiers or the unique properties are changed or reversed, we would be able to anonymize the code or the binaries. The most problematic or difficult, challenging part here is coming up with recommendations to tell people how to change or substitute their code. It's easy to identify what to change, but how can we tell them which exact disassembly instruction to use, or which control flow graph features to bring, and so on. And at the end, our ultimate and most practical goal is to be able to identify the authors of malware and do malware family classification. And we started looking at data sets for this problem. And we started our first steps towards this direction with looking at obfuscations, because malware is most usually obfuscated. And now I would like to give some examples about how this authorship attribution or attribution problem has been perceived by the security community. For example, Bruce Schneier, he's a security expert. He has a blog and he blogs about important and recent topics. And here is what he said on the Sony breach. You might be remembering the Sony breach from a few years ago, and it was attributed to North Korea. And here Bruce Schneier is saying that, whose job was it to defend Sony? Was it the US military's because it believed the attacks to have come from North Korea? Was it the FBI because this wasn't an act of war? Was it Sony's own problem because it's a private company? What about during those first weeks when no one knew who the attacker was? These are just a few of the policy questions that we don't have good answers for. So these are some policy questions we can think of when we're dealing with attribution. And here in this example, we see that the attribution has been made to another country. So what happens if it's within the US? So what happens to policy versus foreign policy? And another thing he said was that in 2012, the US Secretary of Defense said that the US, and this is presumably the NSA, has made significant advances in identifying the origins of cyber attacks. So this is not very clear because when we are talking about the NSA or the military, we don't know what their sources are. They don't want to tell us what their sources or what their methods are because then those can be exploited. And here in this case, we are wondering, did they have some fundamental technological advances, or is it just that their espionage became so sophisticated and advanced that they can tell how an attack is being planned, and is that how they are able to attribute this? So what's going on? We don't really know. And at the same time, it has been said by US government officials in the past privately that they solved the attribution problem. But we don't know what they solved. We don't know how they're doing this. So some transparency here might have been helpful for the policy community to analyze this or to come up with maybe alternative solutions. And some of you might remember this as well. There was the OPM breach, and this is the Office of Personnel Management data breach. This was federal government data, and it included data from 22 million federal employees who went through background checks, and they might not be current employees or they might be past employees, and their family information and a lot of personally identifiable information was involved in this as well. And this was one of the largest government data breaches that happened in the US. And the everyone suspected that this was done by the Chinese government. But then the head of NSA and the head of US Cyber Command said that, I think, first of all, I'm not getting into the specifics of attribution. That's a process that we are working through on the policy side. There is a wide range of people, groups, and nation states out there aggressively attempting to gain access to that data. And in this case, in the OPM data breach, they had to insert some malware so that they can get access to backdoor in the system. But we don't really know how they were able to think of China as the actor behind this data breach. And here we are wondering, what are these specifics that he doesn't want to get into? Can we have a little more transparency? Because this doesn't have to be always about the federal government. This can be a private company, this can be an individual. So how are they supposed to react, or what are they supposed to do in these situations? And also here we are seeing that this is affecting foreign policy because this is coming from a different country. And we would like to find out, how do they do this? Is this technical attribution or political attribution? Who is the one to get blamed at the end? Is it the hacker that's sitting behind the computer to steal all of this data? Or is it political attribution that's necessary? Is it the government that hired that hacker so that they can get that data? But unfortunately, we don't have many answers to these questions. And at the end, a few months after the intrusion was detected, the Chinese government announced that they arrested the hackers that were responsible for the OPM database breach. And a few months after that, they are celebrating with Obama. They seem to be okay with everything, but we don't know how they were able to find these hackers and arrest them. Like, are these real hackers or are these sock puppets? We don't really know what happened, and there is not much transparency again in this area. And I was thinking that after the presentation, maybe we can discuss what has been done in this area before and how this can be improved for the general public. And I would like to thank all of my collaborators for this exciting work. Without them, none of this would have been possible. And if you would like to play with programmer de-anonymization, you can go to my GitHub account and you will find the code for source code authorship attribution and also binary authorship attribution. And if you want to find out the details about these projects, and like there's much more detail about in the publications, you can go to my website and check the publications, and you'll get a better understanding if like there is something that you don't clearly understand. And if you are watching online and you want to discuss something or make a comment, you can go to our blog, Freedom to Tinker, and you can find my blogs about programmer de-anonymization and write your comments there if you want to start a discussion. And thanks for coming, and I would be happy to take any questions now.